to discuss Spring with immutability. And this presentation really was born out of another presentation that I've given for a couple of years now. And that presentation is actually called Effective Java Reloaded. And so when we did that presentation, I took several of the topics in Josh Bloch's book, Effective Java, and presented them in an a la carte style. So the folks who were sitting in the audience were able to say, okay, this is what I want to cover right now versus this is what I want to cover later. And one of the topics that came up several times was this idea of programming with immutability, or as Josh Bloch states it, minimizing mutability, which was item number 15. And you can actually go check out a version of this presentation on InfoQ. And so when we covered that topic, we were able to spend about 10 minutes maybe on it. And as we gave that same presentation in several different settings, the same types of questions and concerns and objections would come up over and over again. And my thought was, why don't we go ahead and do a presentation where we deep dive into these same issues and confront several of those different areas head on? And so what I'd like to do at the outset is walk through the same slides that I would walk through as part of Effective Java Reloaded and allow that to frame the discussion so that we can step into those same issues that we would hit on the sessions in Effective Java. So when we talk about minimizing mutability, obviously we want to talk about maximizing immutability. And so the first question you have to ask is, well, what does immutability mean in Java? What's a mutable class? Well, a mutable class is obviously simply a class whose instances cannot be modified. We create an object, and the state that's in that object is fixed for the life of that object. And so the first question that we like to ask is, well, who's programming with immutable classes every day? And if you're thinking about that, you should immediately say, yes, well, I'm programming with immutable classes every day. I think probably everyone listening is using, at some point in their program, java.lang.String. And so immediately we can kind of put our minds at ease of it and say, okay, immutable classes aren't that scary because that's something that we're all using. Many other immutable classes that you probably use without thinking about it. Think about the box primitives, the integer, double, also big integer, big decimal. And so when Josh frames this discussion, he makes an interesting statement. He says that immutable classes are actually easier to design, they're easier to implement, and they're easier to use than mutable classes. And in fact, they're less prone to error and they're more secure. And so those are some big promises. And so it'd be interesting to walk through why that might be true and what are the features of these constructs that bring that to the table. So the first thing that Josh likes to do in a lot of his items is to present a recipe. And so he gives us a recipe for what it means to build an immutable class. And so the first thing that we have to do is get away from this idea of providing mutators, which that means for most of us, we don't get to write setter methods anymore, which means we're not writing Java beans anymore. The whole Java bean pattern or convention is kind of out the window at this point. We also need to ensure that the class can't be extended. The reason for that being, if I had a subclass, that subclass could see the internals of the class and possibly modify some of that state. And obviously, if we're immutable, we don't want to allow any of that state to be modified. Third, we have to make all of the fields final. Now, this is obvious. We want to make all the fields final so that we can't reassign any references. If we could reassign references, obviously we could modify state. But less obvious is making all of the fields private. Why would I want to do that? Why would it not be okay for me to directly access something like foo.bar? Well, the reason for that is foo.bar, what's the object that reference points to, itself might be mutable. And so let's say we have a date as part of our object components. If I could not change the reference to the data object, but I could change the internals of the data object, I would then also have some amount of mutability that would be introduced into my class, and obviously we can't have that. The final leg of this, though, is to actually ensure exclusive access to any of the mutable components. And so even if we make that date final, even if we make that date private, if we don't, in addition, make that date protected, so any getter methods that might expose that, if we don't actually make defensive copies of those mutable components, we're also going to run into issues. So here is an example of an immutable class that follows the recipe. It represents an instance of the complex number. So if you remember maybe from your basic algebra classes, this idea of a number that has a real and an imaginary part. And so that's what this class represents. And we can walk through and kind of go through the recipe in our mind. We don't see any mutators here. No setter methods. We don't see a class that can be extended. It's actually final. Another way we could have done that is providing only a private constructor. We also notice that all of the state is initialized as part of the constructor. We notice that our fields are private and final. We notice that our accessors are actually returning primitive values, so we don't have to worry about defensive copying. And finally, look at the methods that are actually there for doing operations. Look at add and subtract. Add and subtract are actually returning a new value rather than modifying the existing instance, which is exactly what we would expect. And so we're starting to move into more of a functional approach where rather than modifying objects, we actually always create new objects and return those. And so the first thing that is said about classes like this is that they're simple. Now the question is, what definition of simple are we talking about? What we're talking about is the idea, if we go back to the history of the word simple and we look at its roots, they actually map to two root words, sim and plex. Sim means one, plex means fold or braid. And so the idea is that we're talking about one thing rather than several interleaved things. Well, when we're talking about immutable classes, we actually want to think about state. And so the question is, how many states can an immutable class be in? Well, it can be in exactly one, the state in which it was created. How many states can a mutable class be in? Well, it can be an arbitrary complex state space. It's effectively infinite within the bounds of the types that we're working with. And so the idea is, which one is it simpler for us to think about? Is it simpler for us to think about one thing, or is it simplest for us to think about infinitely many things? And this becomes important when we start to think about the idea of program correctness, which we'll get to in a little bit deeper way later in the talk. Because these are in a fixed state, they're inherently thread safe. We don't have to synchronize any of the access to the state because it can't change. There's no way for multiple threads accessing these objects concurrently to corrupt the state. And so it turns out this is the easiest approach to achieving thread safety. You don't have to worry about learning concurrency patterns. You don't have to worry about learning the actor model, software transactional memory, anything else. If all of your state is actually immutable, you actually have a very easy way to write concurrent programs. And so because we can't corrupt these objects, we can actually share these objects freely. We don't have to worry about what threads gain access to the objects because they can't change. And so because they can be shared freely, in many cases, we'd like to share them freely. So one thing that we might do if we were dealing with the complex numbers is to say, okay, I'm probably going to need to use the values 0, 1, and I quite often. Why don't I go ahead and create constants for those and share those throughout the app? If the value associated with 0 can never change, why would I ever actually need more than one object to represent 0? But it actually gets deeper than that. Not only can I share the objects themselves, I can also share their internals. So if we were to dive into the JDK source code and crack open big integer, we would see that big integer uses a sign magnitude representation internally. The sign of the number is represented by an int. The magnitude of the number is represented by an int array. As it turns out, it's the big Endian binary representation of the number. Now, big integer has a negate method. When we call negate, negate is going to create another big integer with the opposite sign of the number. So it's going to have a new copy of that variable associated with the object. But then it's going to reuse the existing magnitude array. And so if we were to imagine an experiment where we called negate on big integer and then called negate again on the result of the previous called negate, and we did that repeatedly, we would create an object graph that looks a little bit like this one. And so we see here 6 different copies of big integer, all of which have their own sign of a number, but all that point to the same magnitude array. And so this becomes very important as we get into larger data structures, this idea of reusing only the components that need to that don't need to change, while creating new copies of the components that do need to change. So these immutable objects actually make great building blocks for other objects. When I create a class, obviously that class is going to have some invariants associated with it. It's a whole lot easier to maintain a class's invariants when you know that its component objects can't change from underneath it. So these make great map keys, they make great set elements, because you don't have to worry about the values changing. And if you actually took a key object and placed it into a map and then made a change to that, you're actually violating the invariance of the map abstraction, which is obviously a problem. There is one major drawback, though. We've said everything good up to this point. There's one major drawback, and that is that obviously, because they're immutable, they require a separate object for each distinct value. There are no circumstances in which we can create a pool of objects that are immutable, because we can never actually reuse an object from that pool for another purpose. Now, why do we create object pools in the first place? I can think of 2 principal situations. One would be, obviously, when creating that type of object is very expensive. This is why we pool database connections. Another being when we're going to create thousands upon thousands of very small, short-lived objects. And so we get into a situation where the garbage collector is having to work very, very, very hard. And so sometimes we might pool and reuse those objects to keep garbage collection down. But in either case, we don't have that solution at our disposal. And so we have to pay this cost now of creating a new object every time we need a new value. And if we start to create operations around our class, and those operations themselves are multi-step, and every step along the way we generate a new object, we magnify that performance problem. So one way in which we deal with this is to create what we call mutable companion objects. Many times that's hidden from us, and so we'll have some mutability introduced into the computation behind the scenes, and then out at the end pops an immutable value. Sometimes that mutable companion object is exposed to us. So when we think about string, we can immediately think of string builder as the mutable companion object. And so we take that builder, we append, and at the end we call to string, and now we have that immutable value. So you get to the end of all of this talk about mutable and immutable objects, and Josh makes this statement. He wants you to assume immutability during design, which is very different from how most of us probably approach the design of our Java code. We create mutable classes today without giving it a second thought. The idea is to completely swap our thinking and actually to create immutable classes without a second thought. That's a very difficult thing to do. You start to try to do that as you're writing code today at work, it's going to make your brain hurt a little bit. And there's a reason for that we're going to get deeper into. But what I want you to start to think about doing is creating immutable classes by default. And only creating a mutable class if you can come up with a good reason for it. When you come up with that good reason, you say that mutability is actually necessary, limit it as much as possible. You've got 10 fields in your class. You identify one that needs to be mutable. Keep the other 9 immutable. Reduce the state space of that class. And a heuristic that you can actually apply here is to make every field final unless there's a compelling reason to do otherwise. Just get used to typing that final keyword before each of your fields and see how far you can get with it. As you start to do this, you'll start to feel some of the benefits of programming with immutability that Josh talked about. And I would wager that as you get used to it, you won't feel the drawbacks nearly as much as you might be thinking you would right now. Now, this is where we would typically stop and move on to another topic, but we get to go deeper today. And so the first thing I want to do is confront head-on this idea that programming with immutability forces us to change the way that we think. You might start to feel like this person here, who everything that they know about programming is actually crawling out of their head, and they've got this big void left behind of how do I solve problems? Well, there's actually a very real reason for that. And the reason is that it forces you out of the style in which you've been conditioned to solve problems. There's a hypothesis out there. It's called the sapirwhorf hypothesis, and basically it states that we're limited in our thoughts by the language that we use. And so when I'm speaking in English, yes, I'm using the English language. But this hypothesis also states that when I think using the English language as well. And so this starts to come out when you see two people talking to one another and they don't share the same native tongue and they start to speak in a common language, and one or both of them is actually thinking in their native tongue and translating on the fly into the common language. And occasionally phrases will pop out that don't make any sense because the idioms don't translate. You can extend that into the way we write code. So you look at the constructs or the meta model in which we work. Not only do we program with mutability, we also think in mutability. And so there's a whole class of solutions to problems that we're used to employing that disappear when we start to force ourselves to program with immutability. And so that's why the pain comes in. So what is this new style? Well, first of all, we have to look at what goes out. What goes out is this procedural style. So as an industry, we're still pretty conditioned to program in this procedural style. And the procedural style admits the existence of, and in some cases encourages us to use side effects in order to solve problems. So if you look at this diagram here, we'll pass arguments as inputs to a procedure call. We may or may not receive a value in return. But what's entirely likely is that we have this whole collection of side effects that ensue, possibly including the arguments themselves, but possibly also including some aspect of the program's global state. And so if we think about this procedure, if we don't have the source code of this procedure, or at the very least detailed documentation, we have no way of knowing what might happen when we make that call. And that makes it very difficult for us to think about, is my program correct or not? You think about the program that you hook the debugger to solve the bug. And when you hook up the debugger, the bug goes away because it adds just enough additional state, just enough additional threading and complexity and ordering of events to the state of the program to make the state you're trying to troubleshoot go away. What style comes in? The functional style, much more controlled. When we program in a functional style, we pass arguments to a function. We always receive a return value. Now, that's important. Notice there are no side effects anymore. If we're only dealing with a mutable state, there's no way for the function to affect its environment other than by returning some value. So functions also always ought to return the same value given the same inputs. So I pass in 1 and 1, and I always get back 2, as opposed to some other value in the state giving me back a different answer based on its presence in the global state of the program. When you build your program up of building blocks like functions, it makes it a lot easier to reason about program correctness as we can easily test all of our functional components in isolation, and then it simply becomes a case of correctly stringing those together into a data flow that gives us the computation that we want. So Neil Ford has this great quote on immutability in his functional thinking argument series, or article series. He says, immutability is the key to functional programming because it matches the goals of minimizing the parts that change, making it easier to reason about those parts. And this is really the end goal for why I would push you to start thinking about programming with immutability. It's really about program correctness. We've had a lot of emphasis on automated testing in the last decade in our industry. But automated testing isn't enough to prove that the programs and applications that we're building are actually correct. If I have 100% test coverage, I can still fail. If I have 100% test coverage and all of my tests pass, but my tests themselves are actually incorrect, all I've proven is that I'm consistently incorrect. And so there's still a certain amount of thinking and reasoning about the program and what it does and how it works that we have to do to ensure that we know that our program is doing the right thing. And so the strategies that I want to give you throughout the remainder of the talk are about easing into programming with immutability. Obviously, you can't, when we get done with this presentation, delete all of your code that's using mutable state and replace it with code that's using only immutable state. What we want to be able to do is to introduce these ideas and constructs into our programs. Along the way, ease into this functional style of programming. You're not forced to change wholesale into functional programming just by employing immutability. And employing functional style also doesn't mean you have to switch immediately to another language like Clojure or Haskell or Scala. What you'll find is that as you start to employ elements of functional style within your existing Java code, it will help you more easily enjoy the benefits of using immutable objects. So that gets us to this background that I gave you at the beginning. I said there were several areas or questions that would often come up. And as I went around the country giving this presentation, I found that they kind of fell into the same three buckets. So what are those buckets? The first bucket is performance concerns. If every mutation that I make to state means copying an existing object and including that mutation, and as my data structures get large, won't that make my program slower and less memory efficient? So we'll address that concern. The second concern is construction of large objects. So if you look at my object model, and each of my objects is several layers deep. And not only that, each of the component objects in that model has many fields associated with it. And I'm forced to initialize that entire object graph through constructors. Won't that make my life harder? So we're going to address that one as well. And then finally, this idea of framework concerns. So when we look at the enterprise frameworks that we've adopted over the last several years, many of them lean heavily on this idea of mutable state. We like to initialize things through setter methods. We like to use no argument default constructors. And many of the frameworks actually compel us to do that. Obviously, in those situations, immutable objects won't work. So what strategies can we employ? So let's start off again with performance concerns. And let's start off by revisiting big integer. I said that this would come up again, and it would be very important. So think again about big integer. We have the sign magnitude representation, and when we repeatedly call negate on the return value of the previous call, we create this object graph where we reuse that magnitude array. And this is a decent performance optimization, but in many cases, unless we're doing a lot of heavy number crunching, we're not going to see a big difference. There is this nagging idea, though, about large collections of objects. Let's say we're maintaining large lists in memory. Let's say we have a list containing 1 million elements. And I want to make a change to that list. I want to add the 1,000,001th element to that list. If that list is immutable, to add that element, I actually have to make a copy of that list and then add a new pointer cell. Well, now, when I add one element to a list, I don't have 1,000,001 pointers in memory. I actually have 2,000,001 pointers in memory. And so you think about starting to process that data structure, even with the amount of memory we're able to get cheaply today, you can see a point that we're going to quickly run out of memory for our programs. And not only that, just the processing of the list as they grow larger can be slow. So Chris Okazaki wrote the book Purely Functional Data Structures, and it's actually kind of a repackaging of his master's thesis as a textbook. Okazaki was an early pioneer in what he called these functional data structures, which have over time evolved to be known by one of their primary features, that of being persistent. So when you hear persistent data structures and functional data structures, in many cases we're talking about the same thing. Now, this has nothing to do whatsoever with data store persistence. So what Okazaki noticed was that many of the useful data structures that we work with in computer science, they assume mutation in place. And because they assume mutation in place, they don't perform well in functional languages that don't allow immutability. And so his work was in finding ways around that problem. So when we think about a persistent data structure, we're meaning only change the effective parts when copying it for a perceived mutation. And the ineffective parts of that data structure are actually going to be reused. So with big integer, it was that magnitude array that we called persistent. So let's think now about a persistent list. And I'm borrowing these diagrams from a fantastic book by Venkat Subramaniam, Programming Concurrency on the JVM. And so he really well illustrates this problem. So let's say we're maintaining a list of the people who are attending this webinar. And let's say that our initial list has Joe, Kim, and Fred. These are the people that are attending. And I need to add Susan to this list. I cannot add Susan to the end of the list. We look at our cells here. We have basically pointer objects. One cell points to the object that represents the person. The other cell points to the next element in the list. Obviously, at the end of the list is Fred. One of its pointers points to Fred. The other points to null, meaning this is the end. And because that is immutable, I can't actually change it. What I can do, however, is add a new cell to the head of the list. Point that at Susan and point its next element pointer to the head of the previous list. So now I have two lists in memory. I have the original list that still exists and contains Joe, Kim, and Fred. I also have the new list, which to me looks like a list containing 4 elements. Really what it is the original list with the other element prepended to it. And so if we can actually always structure our operations around the head of a list, we can actually use immutability and also have some efficiency in our computation. Unfortunately, we can't actually structure all of the operations we want to perform around the head of a list. We need a data structure that is more flexible and also more performant at the same time. And so what we can actually go to is the persistent hash tree. A tree will actually allow us to model almost any data structure that we'd like to create. So Phil Bagwell did a lot of work around trees with high branching factors. When I say high branching factor, I mean 32 or more children per node. In this case, we have up to 3 children per node. So imagine this tree having 32 or more children. When you start to pile a lot of elements into this tree, what you see is a very wide tree and a very shallow tree. And in fact, you can represent 1 million elements in such a tree at most 4 levels deep. So what we're actually representing here is, again, an ordered list of meeting attendees. And the key in this tree determines the path to the element, and the path to the element is in base 3. So if we look at Bill at the bottom of our tree here, he's at the 9th position in the list. 9 in base 3 is 100, and that allows us to, traversing the leftmost path as the lowest index path, find our way through the tree to Bill. Now, Bagwell's trees were not immutable, but when Rich Hickey created the closure language, he used a variation of these to create a persistent hash implementation. And so now, how do we modify? How do we add someone to this list? We actually do it using a path copying algorithm. So let's say Sam shows up to the meeting, and we want to add Sam to our list at index 10. Index 10 happens to be 101 in base 3. When we trace 101 through our tree, we find out that Sam should actually be a child of the Sarah node. So what we do here is make a copy of Sarah, so you'll see Sarah with a double border now, and then you'll also see the original Sarah with the dashed border. What we're doing here is creating a copy of Sarah. We're pointing this copy to Sarah's original children, which in this case happen to be Bill, and adding Sam. Now, because we copied Sarah, we also need to make a copy of Sarah's parent, which happens to be Jill. So we create a copy of Jill. We point that copy to Jill's original subtrees, which happen to contain Brad and Kate, and then add Sarah. Well, because we copied Jill, we also need to copy Jill's parent, which happens to be the root of the tree. We make that copy. We point the root to its original subtrees, which contain Joe and Bob's children, and add Jill. So what we've done now is to create a new list, a new tree, a new 10-element list that has a new root and reuses all of the previous elements that didn't need to change, only changing and adding elements that were new. And so in this case, to modify a 9-element list and make it into a 10-element list, we actually changed 3 elements. Again, broaden this out to 32 children, and you'll get approximately the same constant time performance. So the next question that comes up is, do I have to go implement all of these data structures myself? Well, absolutely not. There's actually good library support in Java around these types of data structures. I'll point you to 3, and then we'll look at 1 in terms of code examples. That one that we'll look at is Totally Lazy, which is a functional library for Java that tries to be as lazy as possible in its evaluation, and lazy evaluation is beyond the scope of this presentation, but I encourage you to look into that and why that would be beneficial. Functional Java is an older library. It has a little bit steeper learning curve than Totally Lazy, but is also very robust in the way it handles functional programming and these immutable or persistent data structures. And then CLJDS is an interesting library, and then it takes the closure persistent data structures and extracts them from the closure runtime such that they can actually be used from plain Java programs. So most of the code examples that we're going to look at this morning are written using the Spock framework. And the reason for using Spock is that it enables us to write tests in a very nice behavior-driven style and remove a lot of the boilerplate that might otherwise be necessary to write those tests. And so a lot of the example code is going to be Groovy, but we're not going to use very many advanced Groovy features. Most of this will just be Java code with some semicolons and some static type assignments removed. So if you're not too familiar with Groovy, don't worry about that very much. So our initial example here is a persistent list. We have a given, a when, and a then section. The given is our start state. So in our start state, we're creating a variable P1 list, and we're setting that equal to the result of calling treeList. treeList is a method from Totally Lazy that we've statically imported to our class, and it's going to create a data structure that abides by the same algorithm that we looked at with the persistent hash tree and the path copying. And so we're going to insert into that tree list 1 element, which happens to be an immutable foo. We're going to create that immutable foo with a builder, and we'll talk more about builders later in the talk, but just assume for now that we have an immutable foo that has 2 fields, bar and baz. Bar is set to 1, baz is set to A. Now we take our when action. Well, how are we going to change the start state of our program? We're going to add another variable, P2 list. P2 list is going to be the result of calling P1 list .cons. What is cons? Cons is adding an element to the head of that list, and so we'll create another immutable foo. Then, what's the outcome? We should have still two lists in memory. We have P1 list, its size is still 1, so we didn't make a change to that original data structure. It has maintained its original state, but we also have another list in memory that is the result of the combination of the first list with the second list, and we illustrate that by saying that its size is 2. Now, we're not going to run any of the code examples in this talk. If you actually look at the then section, those are the equivalents of asserts. And so anytime you have an assert, we're making a statement that we're going to assume would be true, otherwise we would get an exception. And at the end of the talk, I'll actually point you to the GitHub repository where you can pull these samples and run them. But as it turns out, because they all pass, the output from the code wouldn't actually be all that exciting to look at. So let's go a little bit deeper. Let's assume we have another tree list in memory that we want to work with, and we want to, not a tree list, but a Java util array list, and we want to take that Java util array list and turn it into one of these persistent lists. So we're going to use some syntactic sugar in Groovy. We're going to use the square brackets there to create a list literal, which actually turns out to be an array list under the hood. We'll put 4 immutable foos in that list, and that's our start state. When we're going to take the tree list function, instead of passing an element to it, we're going to pass a list itself. So anytime you pass an implementation of Java util list to tree list, it's going to wrap that in a persistent list implementation. So then we can start to work with that list as if it's a persistent list in the then section, asking it questions like, what's your size, which should be 4? What is the bar value of the head of the list? If you look at the head of this list, the first element has a bar value of 1, and so that should match up. And then we'll go a little bit deeper. Give me the baz value associated with the head of the tail of the list. So the tail of the list here is represented by the 3 other immutable foos, starting with 2, 1, and 1, and the baz values B, Z, B. And so if I grab the tail of that list, then take the head of that, the baz value should be B, and that matches up with our expectation. So now let's do some actual computation. If you start to think about what types of computation we do, most of what we can do is one of 2 types of operations. We either filter data structures or we summarize data structures. So let's do filtering first. Let's take that same list in our given state, that same Java util array list, and wrap it in a tree list. In our when operation, what I want to do is filter this data structure down to everything that doesn't have a baz value of Z or A. So to do that, I'm actually going to call the filter method on plist. Filter takes a single argument, which is a predicate. And that predicate is going to tell filter, here are the things that I want to pass the filter. Everything else should disappear. And so we implement here that predicate as an anonymous inner class, type it as an immutable foo, which gives us a matches method that takes an immutable foo, and we're going to return from that other.baz is equal to Z or other.baz is equal to A. So if in either case that's true, it's going to remain in the list. Otherwise, it will be filtered out. When filter does its work, it's actually going to create that new list out of the original list without modifying the original list. And so if you think back to our path copying algorithm, rather than adding elements to the tree, we're actually going to be removing elements from the tree. And so when we get to our then section now, we see that the original list size is still 4, the filtered list size is 2, but it's still based on that original structure. So now let's look at summarizing operations. Again, given state, the same data structure that we began with. So 4-element list, we're going to create a tree list from that. And what we want to do now is a summarizing operation, which is to take the sum of all of the integer values associated with bar. The way we're going to do that is with a fold operation. Fold operation takes essentially 2 arguments. The first is a seed element. That seed element happens to be the identity operation associated with the function that we want to perform. So since we're going to do addition and the identity for addition is 0, that will be our seed value. And the second is a function that we want to call here, structured as a callable to. A callable to is just a function that will take 2 arguments and return a value. Those 2 arguments happen to be an integer and an immutable foo, and they'll return an integer. When we implement that anonymous inner class, we're going to get a call method. That call method takes an integer a, an immutable foo b, and returns an integer, and that computation is going to be a plus parsing out b.bar. So think through the computation now. We start with 0, and we pass in this callable, we pass into that the first immutable foo in our list, which happens to have the bar value of 1. And so 0 plus 1 is 1. We're going to return 1. That 1 will be passed in as the next call to fold. And so now fold will take 1 and the second foo in the list. Its bar value is 2. 1 plus 2 is 3. That 3 will be passed in with the next foo. 3 plus 1 is 4. That 4 will be passed in with the next foo. 4 plus 1 is 5. And so our then assertion there that sum is equal to 5 actually matches up with what we think happens when we run through the computation. So that gets us to the end of the idea of how we handle performance issues. We don't have to worry anymore about large data structures causing us either memory shortages or slow performance, because we're able to use algorithms that will, A, reuse existing components rather than copying components needlessly, and also because of the way the data is structured and the way the operations are implemented, actually do that in an efficient and sometimes a constant time manner. And so this allows us to have not only the correctness associated with immutability, but also the performance often associated with mutability. So now let's move into the second big issue, and that is the construction of large objects. There's actually a pattern that is called out in effective Java called the telescoping constructor pattern. And that pattern is best illustrated with this class, telescope. So we have here another immutable class. That immutable class happens to have 3 required fields, A, B, and C. It also has 3 optional fields, D, E, and F. And so we think of this as a telescope that's fully expanded. Our first constructor is the fully expanded telescope, and it will actually initialize all of the required fields and all of the optional fields. The next constructor that we see on the screen is actually the fully collapsed telescope. And so it initializes only the required fields and none of the optional fields. And it does that by calling the fully expanded constructor, passing null for each of the optional fields. The next constructor down is expanding the telescope by 1 element. And so we now initialize 4 and leave out 2 of the optionals. And so we can take this pattern and we can follow it for any class that we create. The problem is, with 6 elements, it's not too terrible. As you start to expand to 10, 15, even 20 elements in a class, it doesn't scale very well. Of course, the first answer is maybe we shouldn't be creating classes that are that fat. But ultimately, that answer is somewhat unsatisfying. We should be able to come up with a solution that will scale as we actually have legitimate needs for classes that are that large. Now, why doesn't this scale? Well, first of all, it adds a lot of noise to the code. As your class grows, you might have numerous constructors that actually don't add any information to the class. It's just more code that you have to scroll through before you get to code that actually does anything interesting. And then if you start to work with constructors like that, it's easy to get confused. As the length of the signature expands, and you start to deal with a constructor whose signature is something like string, 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 int string, boolean string, string, int string, well, which string am I actually dealing with at this point in time? And if I need to refactor that constructor, how do I make sure I keep things in the right order? So it gets very difficult to write good, correct, clean code that's easy to read. As it turns out, this is actually why we had, one of the reasons why we have the Java Bean pattern in the first place. Let's give a default constructor and initialize optional fields by setters. And that worked very well for solving that problem, but obviously we've already stated with immutable classes, we can't actually use this Java bean pattern. But there's another pattern that can help us, and that is the builder pattern that we've alluded to in the earlier code examples. So the builder pattern is a design pattern that's intention is to abstract away the steps associated with constructing objects so that different implementations of those steps can construct different representations of the objects. And often that pattern is used to build products in accordance with what we call the composite pattern. So let's drill into the builder pattern a little bit more detail. And the way it's actually stated to us in item number 2 of effective Java is that the builder is a static member class of the class that it builds. And what it allows us to do is simulate named optional parameters. Named optional parameters meaning I can actually give to a function or method not only the argument value itself, but the name associated with it. And that removes the necessity to order the arguments and also removes any ambiguity from what value goes with which argument. And we can't do that in Java. We can do that in some languages. And this actually gives us some amount of simulation of that. And it also allows us to provide some upfront validation before we construct what it is that we want to build from the builder so that we know that the thing we're going to construct is actually a valid object, which is the goal of the constructor in the first place. So let's look here at an immutable foo class that we used in the earlier examples and see what its builder looks like. So the first thing I want to point out to you is that we have this constructor at the bottom that takes a builder object. And in that constructor, it copies the values of bar and baz associated with that builder into the references bar and baz that are associated with the immutable foo itself. Now, where does that builder come from? What is that static member class? So we have here builder. This is immutable foo.builder. It has bar and baz that are our typical mutable fields that we're used to. And we have two methods here, with bar and with baz. What are with bar and with baz? They're sort of setter methods. They take in the value that we want to store, but then they return the builder itself. And so what this allows us to do is to chain calls to with bar and with baz, thus stimulating that idea of named optional parameters. At the end of that chain, what we would call the build method. The build method here calls validate. If you look at validate's implementation, it's using the preconditions class from Google Guava to make sure that bar and baz are not blank. And once we've validated that, we're going to return a new immutable foo and pass in this. So we're calling that constructor that takes the builder, and the result of the whole chain of events is a properly constructed immutable foo that we've built up incrementally. And so this builder becomes the mutable companion object for immutable foo. And it allows us to write code like this. So we have, again, a Spock specification here. In the given state, we're going to create a new immutable foo.builder. When we take that builder and we call with bar 1, with baz a.build, we should get back an immutable foo that itself has a bar value of 1 and a baz value of a. Now, the problem that we've created here is we've simply traded one set of boilerplate for another set of boilerplate. We've stopped writing telescoping constructors. We've started writing these large builder classes. Well, we can get some help from an Eclipse plugin that also happens to work in STS that's called Bob the Builder, Spring Tool Suite being STS. So Bob the Builder is simply a drop-in. You pull the jar, drop it into your drop-ins folder, and it's going to add an icon to your toolbar in Eclipse. So here is the mutable foo before we actually add the builder to it. And so we're going to click on Bob's head there, and that's going to give us a dialog. And in that dialog is a list of all the actions that the plugin wants to take in order to create the builder class for immutable foo. And it even allows us at the bottom to select what Java library, either Google Guava or Commons Lang, that we want to use to construct that validation method. So if we were to take its suggestions and just click Bob Build, we're going to get added now to our class, first that constructor, immutable foo, that takes the builder, and that static member class, the builder itself. Now you'll notice probably right off the bat that this builder class looks exactly like the builder class from the previous slide. And that's because it is the builder class from the previous slide. So what I gave you initially was how effective Java item 2 suggests that we write builders. Bob the Builder actually implements that pattern directly. And so you can have some assurance that you're creating builder classes in accordance with sort of the codified best practices associated with the Java language in effective Java. So that's one way that we can handle this. I want to show you another way. I want to take another trip off into the Groovy language. So Groovy actually gives us a very nice way to create builders as well, particularly as it relates to large nested object graphs. So let's take a look at a typical object model maybe. We have here a person class. Person has a first name, a last name, and an address associated with it. And that address itself is also a large object. It has street number, city, state, zip. It also has 2 phone numbers. Those phone numbers have their own data associated with them, area code, prefix, and line number. So if I were to build this object graph up in memory, particularly in my testing code, I have to start at the bottom, right, and then work my way up to the top. And it's not very intuitive to read through the code and understand what kind of graph I'm creating. What I'd really like to be able to write is code that looks like this. So we have here some Groovy code that starts with a person builder and calls .person and passes to that 2 sets of named arguments, first name John, last name Doe. We're then going to open up a set of curly braces to indicate that we're going down one level of hierarchy. And in that level of hierarchy, we're going to create an address. That address is going to have several named optional parameters associated with it. We'll then open up curly braces again, go down another level of hierarchy, and call home phone and mobile phone to construct those phone numbers. So when you look at this code, it's very easy to see what type of object I'm creating, what the various levels are, and how they relate to one another. So the interesting thing is, though, that this person builder object is calling methods that actually don't exist. So the person method, the address method, the home phone and mobile phone methods, they don't exist at all. So we have to ask, where do they come from? So we'll create a class called person builder, and person builder is going to implement a class from the Groovy library called builder support. Builder support is essentially a state machine that governs the behavior of a Groovy builder. So to construct this object, we're going to think of 2 different types of nodes in our graph. So we have the root of the tree, which is a person. We have inner nodes of the tree, which happen to be addresses. And then we have leaf nodes of the tree, which happen to be various phone numbers. So to represent the root and inner nodes in our builder state, we're going to use expando objects, which are similar to a map. I can add properties and methods on the fly, and that object's going to expand. And then I have leaf nodes here, which happen to be the objects themselves. And so we're going to use the phone number object itself to represent those. We'll implement a constructor for person builder, and in that constructor, we're going to initialize the address and person expandos to be new expandos. And then immediately, we're going to add to the person expando a new method. We do that simply by setting the property build equal to a closure. And in that closure, we're going to call the Java constructor new person, and we're going to pass in the values first name and last name copied from the person expando. We'll do the same thing with address, and then we'll set the home phone and mobile phone objects that presumably already exist. They've been created somewhere else in the builder. And so when you look at this build method, it looks very much like the private constructor we saw that took the builder as an argument in the earlier examples. Now, builder support has several methods that we can override for various purposes. So for our builder, we actually only need to override one. That's create node. Create node takes 2 arguments, a name and a map of attributes. So I said we were calling methods that don't exist. When we call methods that don't exist in Groovy, those get intercepted by a method called method missing in terms of the dispatch algorithm of the language. When method missing gets called, it gets to decide what to do with that method call. In this case, method missing is going to call create node. And to create node, it's going to pass as name the method that we called that didn't exist, and any arguments that we pass to that method that didn't exist will go in as a map of key value pairs in the attributes variable argument. So now you look through our if then else, we call person. Well, we find person in our else if, and that's going to call a method called fill expando properties. It takes the expando that's our target and the map of attributes. We look at the fill expando properties method, and what it's doing is using the iterator each that's associated with attributes to iterate over each key value pair, and then add to the expando a property whose name is the key. And so we're evaluating that key here and setting a property named after that key. And to that key, we're assigning the value that was the value associated with that key in the map. And so we do that for each of the arguments in the list and return that expando, which results in an expando that's fully populated. For the home phone and the mobile phone, we're simply calling this build phone number method here and populating the objects at the bottom of the tree. And we could actually think about a refactoring to this code that would handle everything with fill expando properties. So once we've created this state machine, we can then write that more declarative code that expresses the levels of our object hierarchy and build immutable objects with Groovy code. Now, obviously, we still have to write this Groovy code, but it is an alternative to code generation in terms of writing fairly expressive builders for these immutable objects. And so that deals with the problem of large object construction, which leads us to this last problem, which is framework concerns. The enterprise frameworks that we've come to know and love and use to get our work done, for the most part, assume mutability in terms of how they work. And the first thing that always comes up during the Effective Java Reloaded talk is, what about Hibernate? Or what about JPA in general? What about any framework that implements that standard? For the most part, we can see that object relational mapping solutions expect us to use default constructors at very minimal. Usually they expect us to use setter methods. They don't work at all with the immutable class recipe that we express at the beginning of the presentation. And it's not just Hibernate, it's any framework that we might employ that would require a no argument constructor or setter methods. And so what I want to look at are two different strategies. The first is a strategy that helps us to take an existing application and migrate it in the direction of using immutable objects, and then also a direction that we might employ if we were approaching a greenfield project. So the first thing I want to point out to you is the bridge pattern. So the bridge pattern is a pattern that actually decouples an abstraction from its implementation. So when we think about abstraction in Java, we tend to think about interfaces and abstract classes. And when we implement that abstraction, we directly implement that interface or we extend that abstract class. And so what we're actually going to do here is introduce another level between the abstraction and the implementation. You can almost think of it in some ways like the adapter pattern. We have this object that's a go-between between the abstraction itself and the implementation. And that allows both of those to vary independently from one another because that bridge translates one to the other. I really like the way that Brian Merrick describes this idea in his book, Functional Programming for the Object-Oriented Programmer, which incidentally, if you're looking to learn functional programming and you come from an object-oriented background, I think it's one of the better books out there. So in his book, he has a diagram that looks a lot like this one. Now in his diagram, we have an object-oriented world, and we have functional nuggets. And so his idea is that we have this large code base that assumes object-oriented design principles. We see some aspects of the problem that we'd like to solve in a functional way, and so we'd like to be able to nest those functional solutions inside this object-oriented world. We're going to look at this in terms of a design that assumes mutability. So we have this mutable world. We would like to solve some problems with immutable objects, and so we'd like to nest those immutable solutions into the mutable world. In either case, the way we do this is by wrapping those nuggets with what's called a restructuring layer. That restructuring layer's job is, as data comes in, to restructure the data from mutable to immutable, allow the immutable nugget to do its job, and then on the way out, restructure the data again from a structure the immutable nugget understands to a structure that the mutable world understands. And so a very good example of a restructuring layer that we can leverage from Java is Dozer. So Dozer is an open source library that is essentially a Java Bean to Java Bean mapper. And what it does is recursively copies data from one object through a mapping to another object graph. And typically what you're looking at is not just single Java beans, but actually a complex network of Java beans. Now, I've said the word Java bean several times. We've already said that Java beans are not immutable objects. Immutable objects are not Java beans, and so we've run into a problem. Now, I wasn't satisfied that Dozer couldn't be used this way. I started doing some experiments, doing some research, and I happened across a very interesting blog entry. The blog is somewhat unfortunately named, but the content's very good. And in the content, it makes the suggestion, well, the immutable object itself is not a Java bean, but its builder looks very similar to a Java bean. So here is immutable foo's mutable cousin. We finally get to meet foo. And foo is our standard Java bean class. It has a no-arg default constructor. It has mutable bar and baz fields. It has getters and setters. This is the Java POJO that we've gotten used to. As a reminder, here's the builder class that we constructed with Bob the Builder for our immutable foo. And so what I'd like to be able to do is map one to the other. So the first thing I need to do is configure Dozer. So what we're looking at here is a standard Spring Java configuration class. So we've annotated Dozer config with configuration. We're going to create a static bean mapping builder, and we're going to implement this configure method. And in the configure method, we're using a basic Java DSL to create a mapping from one class to the other. So our mapping takes foo.class as one of the elements we'd like to map, immutable foo.builder. Remember, we're going to use the builder here. And for that pair, we're going to continually call fields. Fields takes the two fields that we want to map. On the left hand, the foo class, we want the bar field. We're going to call its set method out as setBar. The right-hand side, the immutable foo.builder, its bar field, its set method is going to be withBar. Now, why do we have to name the field twice? Well, if this is a general mapping solution, we could be mapping a field with one name to a field with a completely different name on the other side. In this case, they happen to be the same. So bar and setBar maps to bar and withBar. Baz and setBaz maps to baz and withBaz. And so given this builder, we then can have a Spring Bean created with our mapper method that's going to instantiate a new Dozer Bean mapper, add to its mapping the builder we just created, and return the mapper. And so now we have this Dozer Bean mapper in our Spring context. We're going to do bidirectional mapping. So we have here another Spock specification, and you can assume that the mapper has been auto-wired into this class. So given we have a foo, and that foo is a new foo that's using your basic Groovy constructor syntax, so it looks like named optional parameters. What it's actually doing is calling the setter methods. So we have a foo with a bar, and a baz. We're going to create an ifoo by calling mapper.map. We pass in the object we want to map, which is the foo, and we also pass in the class that we want to map that to, which is, remember again, not the immutable foo itself, but the immutable foo's builder. So mapper.map foo to immutable foo.builder, that's going to give us back an instance of the builder. We call build on that. In our then section, we can then compare bar and baz for the immutable foo with bar and baz from the foo. And so this proves to us that we can map a foo to an immutable foo, but our map also allows us to go the opposite direction. And so again, we have the mapper auto-wired into the class. We instantiate an ifoo, an immutable foo, with its builder, so with bar, bar, with baz, baz, call build on that. That gives us an immutable foo. We pass that immutable foo into the mapper and foo.class, and we're going to get back an example of a foo. And so now we've shown an example of a very easy to create restructuring layer that allows us to go from a mutable world into an immutable world, solve a problem, and then take the result of that solution and map it back into a mutable world so the rest of the program can consume it. So if you want to introduce some amount of immutability into your programs today, this is one way that you can get that done. But let's assume now for purposes of argument that we have a greenfield project. And on that greenfield project, I'd like to embrace immutability from the start. Are there any frameworks that are starting to support immutability today? As it turns out, there is one relatively young framework called Germ, which is a Java immutable object relational mapper. And the idea here is to have an object relational mapper similar to what Hibernate or MyBatis or others do, but have it work with immutable objects directly. And so the way it does this is to actually take care of the mapping from objects to SQL or SQL back to objects, and then in addition, delegate the rest of the actual persistence operations to Spring JDBC. Now, why is that important? Well, it's important because Spring JDBC happens to be probably the most stable, mature, robust JDBC mapper that there is. And because we're using that with Germ, we're actually not reinventing transaction management, state management, AOP. All of that is actually baked into Spring JDBC and the Spring framework for us. We're just using Germ to negotiate the mapping between the objects and the SQL itself. So how would we leverage Germ? Well, let's take a look at another Spring configuration class. So in this Spring configuration class, we have a property source that's going to pull in our JDBC properties from a prop file. And we create a driver manager data source just like we would today. We create a data source transaction manager that consumes that data source just like we would today. And so the only real Germ addition here is a Spring bean called Spring Germ Factory. So we'll create a bean method for that, and we'll return a new Spring Germ Factory that consumes that data source. And so now in our Spring context, we're going to have this Germ Factory that's capable of creating data access objects for Germ. Here is our immutable class that represents, in this case, a speaker at a conference. You'll notice that this immutable class is annotated with JPA annotation. So speakers will be stored in the speakers table. The ID is represented by the ID field. And so we use JPA annotations on our domain classes just like we do today. One additional point of annotation that we have to do is on the constructor itself. It's not possible in Java to actually reflect on constructor arguments. And so we need a way for Germ to actually map between its intermediate representation, SQL to an intermediate representation to the constructor and back. And so it's actually going to use JSON as that intermediate and use Jackson to do that mapping. So we have here Jackson mappings indicating that this speaker is a JSON creator. So I can create JSON from the speaker object, and I'm mapping all of the names of properties in that JSON object, ID, name, and title, to the ID, name, and title argument on my constructor. And so that allows Germ to actually map back and forth between this immutable class and SQL. So how do we actually use it in terms of data access? So we're going to look at a few more Spock specifications. So each of these is going to leverage a particular application context. They're going to pull in a transaction manager, and they're going to be transactional. So every time we run one of these, they're going to roll back. We're going to auto-wire in the germ factory that we created. And so now we're going to create a speaker in the database. So our given section, our start state again is we need a DAO. So we're going to call factory.dao4 and give it that speaker class, and that's going to create a DAO object that can work with speakers, which are immutable objects that are annotated with the JPA and Jackson annotations. We'll create an ID for the speaker that we want to store. In this case, we're just going to call random UUID. And then we're going to create that speaker object and give it an ID, give it my name, and give it one of my former titles. Now, when we insert that speaker, dao.insertSpeaker, so it looks very much like how we might use Hibernate today. We call dao.findById to get that speaker back out, compare the two objects based on the logical equality, and we see that one is actually equal to the other. And so the way we leverage germ and immutable objects looks very much how we might leverage Hibernate and mutable objects. Let's do an update operation. So given state, the same as before, get a DAO, get an ID, get a speaker. We're going to, in the when block, insert that speaker. We're going to call update, and we're going to select a property that we want to set. So we're going to set title equal now to senior architect, where property ID is going to be equal to the ID that we just created. And that's going to generate some SQL we call execute to execute that update statement. We then call dao.findById again, and we compare the titles from the original object, which we still have in memory, with the new object, which we now have in memory by pulling it from the database. So this illustrates that germ is actually not stateful, it's stateless. If we were doing this with Hibernate, we would actually have updated in place, so we're not updating in place here. So now let's look at some query. We're going to, again, create a DAO for speaker, and we're going to insert 4 speakers in a batch. So in the when block, we have dao.insert. We give it an iterator and a batch size, which in this case happens to insert everything in the iterator because the batch size is equal to the list size. We're then going to call dao.select.where.property name is equal to Brian Slutton. So in this case, we want to pull back just speakers that have the name Brian Slutton associated with them. Run that query and give that back to me as a Java util list. So then, based on our data set and our query, we expect the size of the result set to be 1, and we expect the title associated with the one result in that list to be Ford Lean Software Engineer, which matches up with our expectation. And so this is kind of the Hibernate criteria style type query, and that allows us to use kind of a fluent interface in Java itself. Obviously, we know that many times that criteria model will break down, and we need to drop to native SQL. And so we have that same option here. Germ has a very interesting way of binding to SQL. So if you look at our SQL and our given statement, we're using the here docs, the 3 double quotes that give us multi-line strings. And so we have select ID name title from speakers where a name like matcher. And then next to that, we have an SQL comment in curly braces that says last name matcher. And so this is a binder for germ, which allows us to, when we down in the when section now, call select builder factory.sql. We give it that query, and then we're going to start to bind things. And so we're binding to last name matcher the actual like string that we want to work with, which happens to match everyone whose last name starts with uppercase S. And so when you call bind, germ is going to look through the SQL for a SQL comment in curly braces that matches what you wanted to bind to, find the thing next to it, and actually replace that. And so it feels a little bit like the more modern templating engines that will give you, for example, valid HTML5 out of the box that you can look at in a browser, but then still do some amount of server-side content generation dynamically. Same idea here. So you can take this SQL, copy and paste it as is into an SQL console and run it, and it's actually going to work. So we bind that, we run the query, we get back on the list, and again we see a result set size matching our expectation. We have 3 speakers whose names start with S, last names start with S. We get back those 3. And so that illustrates a little bit of how you use germ. And the nice thing about it is that it's actually not that fancy. It's not that different from what we're used to, which allows us to kind of use a familiar paradigm while at the same time leverage in our persistence model the idea of immutability as well. And so we've now kind of dealt with the 3 big issues that tend to come up: our performance issues, our construction of large objects, and then just some idea of what it looks like to use frameworks like Spring and Hibernate in the face of these immutable objects. So that's all of the content that I brought this morning. You can get to all of the code samples for this presentation at github.com/mstine/immutability examples. And the only requirement there is that you build those and run those with Gradle. And then if you wanted to check out an example of the Effective Java Reloaded presentation itself, I also embedded the URL for that, infoq.com/presentations/effective Java techniques. And so with that, I'll hand it back over.
Thanks, Matt. So I think, I know we ran a little over time, so we don't have a lot of time for questions, but I think we're lucky because I think we've managed to exhaust everything in the question queue. So if there are questions, now is the time to enter them into the chat panel. If not, we'll give it a moment just to see if there are any takers. If not, we'll wrap up the session because we've been able to address all the questions during the webinar in the chat. So, let's see, Matt, would you, leave up that slide exactly? Okay, thank you. And while we're waiting for any questions, just want to let you know that we are having some pretty big webinars coming up in January. We're going to be having none other than Jürgen Höhler speak about the launch of Spring Framework 4 on January 9th in the new year. So that's going to be our first webinar of the new year. That's going to be followed, I believe, on the 13th, if memory serves, by Rob Lynch talking about Spring Security 3.2, which is designed and meant to run with Spring Framework 4.0. So some pretty big webinars coming up in January. We hope to see you there. This is being recorded and will be available in less than 2 weeks. Often I try to get it done within a few days. And that will be posted to spring.io/video, which is a redirect to our YouTube channel. If you want to be notified about the publication, easiest thing to do is subscribe to the Atom feed at spring.io, and you'll get notified about the webinar replay as well as upcoming webinars and other great blog posts and things like that from our engineers. And other great content like Spring 1, 2GX video replays and all that kind of good stuff. Alternatively, if you just want the videos, you could subscribe to the YouTube channel if you want a notification. Great. That's pretty much it. Matt, any concluding comments before we wrap it up?
No, I think I've shared everything that I had this morning.
Wonderful. Okay. Thanks so much for your time. Great. Thanks to everyone for attending, and we'll see you hopefully at the next webinar. Have a great day.